This is Tony Pabbert. I'll be your host. Tonight's class features Bruce Director on fundamental scientific breakthroughs in a second Trump administration that we're on the way to major engineering type breakthroughs in space travel, in nuclear power, in fusion power especially. But it's less understood that we're also at the point of fundamental breakthroughs in basic science. And we discussed that in terms of a fuller understanding of biology and of physics, putting behind us reductionist science. And one thing we cited in the email publicizing the show, what is the fourth scientific method beyond partial differential equations, statistics, and computation as scientific methods? So with that, let me bring on Bruce Director.
Well, hi, Tony. It's good to be with you. Yeah, as you mentioned, there's a lot of excitement about the engineering and technological breakthroughs which are under development and to be developed with a new Trump administration. I guess most of our viewers tonight saw the really spectacular launch and recapture of the Starship last Sunday. There's a lot of excitement also last week because Elon Musk, who seems to have an infinite capability for invention, had a rollout of Optimus robots and his self-driving robo-taxis, and he put that together with his Cybertruck and his Neuralink, and that's just the stuff he's doing, which of course is quite dramatic because so much of it is being accomplished by one person or at his initiative. But also that's not the only thing that's going on. Really major new technologies and scientific engineering capabilities, which really have the potential to completely revolutionize our lives and revolutionize the economy in ways that right now you can't even conceive of. And history is replete with these kinds of examples. But there's another side to this thing, which is that science is really hamstrung right now by the prevailing structure of scientific inquiry that really, I guess, goes under the umbrella of the idea of reductionism, which is what everybody believes. And what I want to talk about tonight is the connection between scientific breakthrough, social policy, and economics. And I think these things go together because everybody's familiar with how the social constraints that have been imposed by the establishment has held back the engineering application, for example, of scientific technologies. For example, nuclear power. Back in the 1950s and 60s, starting in the 1950s, but especially in the 1960s and 70s, nuclear power was the energy of the future. It was supposed to be too cheap to meter. We were going to break free of having to generate electricity from fossil fuels, which would have saved those fuels for industrial processes and generated our electricity, unlimited amounts of electricity with nuclear power. And there was no reason why that couldn't have continued cheap, abundant nuclear power. but then based on the social policy of the environmentalist movement, which was really not an environmental policy, but was a policy of enforced deindustrialization. It was intimately connected with what later became known as globalization. That is, the idea was to deindustrialize the economy and to brainwash people to hate technology, and so nuclear power died. Now there's a certain comeback of nuclear power, mainly because the software companies need huge amounts of electricity to be able to power data centers and AI. So people are now talking about nuclear power again. And of course, there have been some engineering developments that the new nuclear power plants are more efficient, better, safer, and so forth than the ones that were built back in the 70s. But you can see that the engineering, the application of existing technologies was held back as a function of a social policy and an economic policy, which was basically, if you know anything about the politics of the last 50 years, was an anti-human policy, a policy of population reduction. I mean, this was all one package. Population reduction, population control, reducing technology, et cetera, et cetera. So, and a lot of people are familiar with that. And you can see this also as the example of what Musk did with the idea of a reusable rocket. You know, our space program was being wound down for social, political, and economic purposes in the 1970s and 80s, and limited to this to very limited technology, the space shuttle, which of course didn't last that very long and was very limited capability. So Musk comes along and designs reusable rocket systems, and upgrades that to the latest one that he's developing, the Starship. And you get a complete redefinition of the economic relationships of space and man's relationship to space. So, and that completely redefined was a interrelated. I guess what I'm trying to say is that it was an interrelated between the development of engineering and new technologies and the social a change in economic and social policy, and this has now come to a head and is a key issue in the election, because we know that if Trump is elected, that this kind of applications will move ahead full steam, and if Harris is elected, it will all come to a halt. Remember that it was Barack Obama who shut down the space program, basically. It said we don't need to do this kind of stuff. So it's a philosophical question, which is what I want to underscore. So people are familiar with that, and we can talk more about that if you want. But what people are not so familiar with is the relationship debate in basic fundamental science, which is really being held back by the same policy. This is a much longer history, going back to really the introduction of the Enlightenment and the adoption of the idea of reductionism, which is largely associated with the Cartesian the ideas of Descartes and Newton. And so we've come to a situation where there's a growing realization that the reductionist approach cannot solve the problems of basic physical biological sciences. And so therefore, even though, and this is an interesting paradox, that even though we're able to make breakthroughs in engineering technologies, which actually are based on new types of applications of physical principles of which we really don't understand, but yet we're able to use them, able to create them. That's not untypical for human progress. And it illustrates something very important about the human mind. So there's a growing realization that we have to rethink our approach to fundamental science. And there's a huge debate in the scientific community right now in which a small group of scientists are confronting these questions and trying to break free from the constraints that are imposed by the scientific establishment and the politics around that, and actually start to really raise questions and try to look for new ways to approach our understanding of science. My thesis, which I want to discuss tonight and hope to have some dialogue on, is that the direction to go, at least initially, is to use the insights that we can gain from LaRouche's ideas on physical economy to try and reorient ourselves and reorient science into solving some of these problems. I'm sure everybody's aware, these things are not, they are very deep and technical, but people are aware of the problems, such as the paradoxes associated with quantum phenomena. Even though the scientific establishment claims that quantum mechanics is the most successful scientific theory, it actually doesn't explain anything about the phenomena at which it purports to explain. Nevertheless, we have the capability to engineer quantum phenomena and put them under our control, as everybody experiences every day when they use a computer or any microelectronic device. Another area, that's an area of basic physics. Another area is the question of biological processes. Modern biological sciences is hampered, really, this is where it really shows up, by a really strong reductionist approach to understanding of life. So much so that even though we've made great strides in diagnostic techniques and discovery of experimental work and empirical discoveries of biological processes, to this day, science really cannot define what is life. They try and give it a fundamental, a definition, and there are many different so-called accepted definitions, but none of them actually describe can actually say what is life. And, this is very easily illustrated, that the modern reductionist idea of life basically tries to reduce life down to a collection of chemical processes that is capable of evolution, and self-reproduction. I think that's the most common accepted definition, or something close to that. But yet you can't really reduce life down to a set of chemical processes. And this is illustrated, very simply by the fact that, a living organism, when it ceases to be alive, for whatever reason, still has the same chemical makeup. All the molecules and atoms are the same, but yet the the living process is not there anymore. Now, in the 19th century, there was a strain of science called vitalism, which tried to describe this, that life was some vital force, but that they had no way to actually explain that. And so this creates a real paradox that we don't really know what life is, and yet we're able to make good strides in intervening on living processes, and we see this in terms of medicine and everything else. So we have to come up with a concept of life as being a state of matter, living systems that we don't really understand. So those are two examples, right? We have, basic physical, the nature of matter itself, which we have no real understanding of fundamentally. We have mathematical equations which allow us to manipulate it, but those mathematical equations do not explain or give us any idea as to what it is. The same thing is true with the example I gave with life. We can know a lot about how life works in the sense of the biological processes that go on in cells, in living organisms, but we don't really know what it means to be alive and how living processes come into existence. What my thinking is that with these kinds of breakthroughs in economy that we can begin to unleash in the if we can get the kinds of policies which Trump says he wants to implement, and we can break down the barriers that have been put up by the scientific establishment, and we get the kind of inspiration in society that motivates people to actually think about these things in a different way, that science will be able to actually make progress on these very fundamental points.
Do you think you could give people any idea of what reductionism is for those who don't know? I mean, you alluded to it through the examples of Descartes and Newton, but maybe you can.
Yeah, that's a good idea. This is very, very important that people understand it. I mean, let me try and do that by example, but the basic idea of reductionism is that a scientist has to reduce the subject of their investigation down to its basic constituent parts. And if you understand the basic constituent parts, then you can understand the process. That's all there is to it. Like, for example, in a simple case, you take Newtonian physics, which reduces the motion of a planet or any body, any physical body, to a set of mathematical laws, such as Newton's inverse square law that says that two bodies have a tendency to attract each other, and the force of attraction is proportional to the inverse square of the distance between them. And it treats the bodies, which are physical things, as if they were points, physical points. However, and when you're dealing with bodies which are very small relative to the distance, this mathematically works out to a very good approximation. That is, if you treat sort of the Earth and the Sun as points, and you estimate their masses, then you can use Newton's equations to calculate the force of attraction and the motion and so forth, without getting too technical, of the Earth around the sun. But that doesn't tell you anything about how the solar system, what is actually organizing the solar system. Because even in the mathematics of Newtonian equations, you can't actually calculate the effect of three bodies interacting on each other. It becomes virtually insolvable. Now you compare that to Kepler's idea of the solar system, in which Kepler asked the question, what is the principle that's governing the organization of the solar system as a whole? And from that standpoint, he asked the question, why are there 5 planets that he could observe? Why are they where they are? What is the nature of their motions? And then he had the benefit of a huge amount of empirical data from especially the observations of Tycho Brahe. And he looked at this and he said, let's take an example. Let's look at Mars and let's try and understand what is actually causing Mars to move in the way it's moving, understanding that the relationship between the Earth, Mars, and the Sun is a relationship that's occurring in a solar system which has an organizing principle. Now, of course, Kepler came before Newton, and I'll explain that in a second. But out of that, Kepler developed, well, there are basically 3 mathematical models at the time that were acceptable, which were all based on some combination of perfect circles, that the Earth, the Mars, and the Sun were on perfect circles, moving on perfect circles. Some of these had the Earth at the center, some had the Sun at the center, but none of them dealt with the question of what is the actual cause of the motion. So Kepler said, looked at this completely differently and developed his idea of the 3 laws of motion of Kepler, especially that the planets move in elliptical orbits, that they sweep out equal areas at equal times, which is another way of saying that the measure of their time is the area swept out, not the motion along their arc, and that the distance between the planets, the relationship between the size of the orbit and the time of motion is in the ratio of the cube to the square. So that's, again, he came up with mathematical descriptions, but the mathematical descriptions were derived from an actual attempt to try and understand the characteristic of what really is the principle that's governing the solar system. And another very important point in this regard is that the solar system is not existing as it exists today, is not the way it always was, that it's an evolving system. And so its characteristics that you currently observe tell you something and are the effect of how it developed, and also tell you something about how it's going to be developed. So the reductionist approach reduces the solar system, in this case, to a series of point masses that are governed by relationships across straight lines, versus the idea of trying to understand what is the basic principle by which the universe, the solar system, is actually organized. Does that make sense, Tony?
Yep.
So another example of this in biology is the reductionist idea of that is, everybody has in their heads about genes and DNA. And we're taught that DNA is a molecule that's made up of 4 amino acids that are put in some type of code that the DNA splits itself and takes its code and encodes an RNA. The encode then the RNA then another DNA molecule decodes this. Is the way that it's said, and that this determines how all biological systems work. Now, a British biologist or physiologist, Dennis Noble, who is a very interesting and scientist who's an opponent of reductionism, makes the point that even though every biologist and scientist and even popular, even laymen, would consider this to be an explanation of how life works as DNA, by DNA, this is a complete illusion. Because as he points out, you could take the DNA out of the cell, put it in a petri dish with whatever nutrients you want, and it won't ever do anything until it's put into a living system. So it's the living system which tells the DNA what to do, not the DNA telling the living system what to do. So we have to develop an approach to science which breaks free from this reductionist idea and actually starts to look at what is the actual development of the universe itself. Because the universe is not a static system. It's an evolving system. And as is evident from the empirical, just the empirical evidence, it's always creating something new. How does life emerge out of non-living matter? How does, and everything you look at in the universe is always in a state of development. It's evolving from one state to another state. Just take the non-living parts of the earth. In the case of mineralization, you have an even distribution of why do you get concentrations of minerals in various parts of the earth? What kind of processes are driving and controlling this process of concentration of chemical compounds into minerals? And what are the processes which control that? We also know from Vernadsky and others that living processes have a lot to do with this, that much of the concentration of minerals have to do with the metabolism by living organisms of certain minerals like iron, and that concentrates the iron into deposits or fossil fuels, concentrating hydrocarbons in places in the earth. So what is the process what is this a process of? Now, the basic approach to this in general today is to try and look at these, as I mentioned, in three basic ways. One is to come up with mathematical expressions that describe the process as a continuous process, which like the motions of the planets. And Kepler called for this, and Leibniz developed it. Newton stole it and invented the calculus to basically give us a way of developing mathematical equations which describe such processes. But these kinds of processes, and I don't mean to be too abstract here, have the characteristic that they don't actually change their mode existence. I take a simple example like a pendulum swinging without friction. Once you set the pendulum in motion, you can calculate using these differential equations the motion of the pendulum at any given point in time. But it's all the values of the equations are all based on knowing the initial conditions, and then that's all that happens. It just keeps going back and forth. Another approach, but then some physical processes can't be understood by such types of equations, like the flow of heat, which goes from hot to cold, or processes like diffusion, where you put cream in your coffee and it diffuses out and so forth. So another approach is statistical approach, where instead of trying to determine the motions of the molecules of cream or your thermodynamic fluids, such as steam or something like that, you take a statistical approach. And then the third way now, which people are coming up with, is to try and understand these things as if they were computers, computational. That there's some underlying algorithm in the universe which is dictating how the universe goes. And these things, and all three really are just ways to give descriptions, but they do not tell you what is the underlying process. They don't answer the fundamental questions. What is life? What is the nature of matter? What is the actual underlying principles that enable the universe to evolve from lower states to higher states and to introduce completely new things which didn't previously exist? Now, I think that the way we can begin to approach these problems is to not look at it from the standpoint of physics and biology, but look at it from the standpoint of economics. And you see exactly the same thing, and this might be easier to grasp from the standpoint of looking at how modern economic theory works. Because if you treat the development of the economy, if you construct an economic model, just try and construct an economic model, you run into exactly these same types of problems. If you try and use statistical methods, you can't model the economy. You can come up with approximations, but they always end up being wrong. If you try and look for some differential equation that, if you know the initial conditions, will forecast the exact effect, progress in the economy, it also fails. And you cannot actually, obviously, you can't treat the entire economy as a big computer, which is just as an algorithm, which is producing economic forecasts based on running a set of complex algorithms in an advanced data processing device. Because the very nature of the economy, of economics, is that it's always changing. And in an economy, the purpose of the economy is to develop completely new things which reorganize the economy completely. Like, for example, the development of electricity. When the people who first discovered electricity in the 18th and 19th centuries, such as Franklin, Gauss, Volta, Ampere, Weber, Riemann, and so forth, they had absolutely no idea that electrification would ultimately completely reorganize the man's relationship to nature and human economy. So how do you mathematically predict something which is completely outside the idea of idea of the basic assumptions that go into the mathematical formulas. So what I'm hoping is that as we remove the shackles from science and begin to get people freed from this idea of reductionism, that there will be a whole renaissance of basic research that will look at these types of, look at the fundamental questions of science in a completely new way. And that's what I'm hoping will come out of the, as a byproduct, or actually an intended product of the revolution in science, which we will see in the Trump revolution. So you may have a lot of questions about that, Tony. I know I was very general, so pin me down.
Well, I mean, I've been reading about, this point in biology. I'm reading, among others, the British physiologist Dennis Noble, whom you mentioned. He in a paper, I may be able to make it available to viewers in an interview, actually, which Bruce also read.
Yeah, I think it'd be good to.
Yeah. Okay, I'll try and do that.
Chat.
He asks briefly. He asks whether there is true novelty in the universe, or whether the universe came into being with its rules and that's it. That's the end of it. So that's, a basic question which Bruce raised really in the case of the economy, because the economy works in reality by means of new leaps in man's ability to act in the universe, is coming ultimately from scientific breakthroughs. But, they're not, each of them is not a scientific breakthrough. Great leaps in man's relationship with the universe, like mass production, as developed in the U.S., from the Remington rifles through Henry Ford and beyond. So this is a big question, and how does reductionism permit? How does the reductionist outlook permit the idea of fundamentally new developments, self-created in the universe, as man does in his economy. And then, going further on this question of reductionism, he asks, why is that man pointing? And he says, well, the man is pointing because there's a thing called intention, and it's not a thing but a process. He says reductionism consists of, or in part, of misrepresenting processes as things, but an intention is not a thing but a process. It's interpersonal. It's outside the body per se, although it's not a ghostly thing. So why he pointed from the intention without the need for records of firings of individual neurons. All this resembles, a dialogue Socrates conducted in his prison cell before. Can't remember the name. Is it Crito? But he conducted his prison cell before the day of his execution.
The Critias, I think.
Not Critias, no, but the one right before his day of execution.
Yeah.
So, he says he pointed because of his intention, and he says, if you locate it in the brain, you misunderstood. And then he takes up the question of ideas. What are ideas? Ideas are real in some sense. They have the ability to make things happen. Mathematics is an idea. Where is it located? So these are some of
Right. He makes
Noble's.
the point. He makes the point that if you were theoretically to be able to identify all the neurons that needed to be fired to make you point, and you activated those neurons in exactly the right way that
Yes,
is necessary to make you point
with electrodes.
with electrodes, and you did that, you would point, but you would have no idea why you pointed.
You would say, I mean, he said the man would say, I didn't point, I was made to point.
Yeah. Now, of course, that assumes that our current understanding of the or this computerized understanding of the brain is true. This is another example of reductionism, that in modern, they do sort of a circular argument here, where they assert that the brain, they look at a computer and they say, we can make this computer stimulate a human brain, human thinking.
Simulate.
Yeah, simulate the human thinking. And we can do that by using a physical process that is semiconductors, and by manipulating voltages, turning on and off voltages as switches, as digital switches in various combinations, because we've learned how to do that and make very complicated combinations of such, that we can create a physical output. Because remember, that's all you have in a computer. The computer is not talking to you. The computer is, when you ask ChatGPT a question, you're typing on your computer, but your keystrokes are translated ultimately down into some type of instructions or to the machine, to the semiconductors, to turn on and off switches. And then when it answers you, after it does whatever it does, it's just putting, lighting up different pixels in the images of letters, which you interpret as words. So the computer is a purely mechanical process. There's no thinking going on there. But because it appears to be thinking, we speak of it as if it were thinking. So we say, since we can make this mechanical process, electromechanical process, appear to be like thinking, that must mean that our thinking works this way.
Yeah, very well said.
So then we take neuroscientists, and they look at the brain, and they see that, well, we have cells in the brain called neurons, which sometimes discharge an electrical impulse and sometimes not. So we can consider that as when a neuron fires, which is basically a biochemical process, and there's an exchange of an ion, which exchanges an electrical charge, that's the same as a switch going on and off. So we call that 1, and when it's not doing it, we call it 0. So now we can construct an image of the brain as if it were a computer. Now, there's two things. I mean, there are many things that show that's completely ridiculous. Because first of all, we know at least the physics of a computer is a solid state process. The biophysics of the brain, neurons are living cells. These are not mechanical switches. And the neurons are not the only cells we have in our brain. There's glial cells, there's all kinds of other processes going on in the brain, which are biological processes that are under the control of life. And the relationship to these kinds of, the physical act of brain activity is completely different. It's an entirely different domain than the behavior of semiconductors. And secondly, there are all kinds of mental processes for which we have no underlying physical substrate. For example, the neuroscientists have been able to, at least in less developed animals, living organisms, but even to some extent in human beings, can get a relationship, for example, between an image that stimulates light, a light stimulation of the retina, and a part of the brain which reacts to those stimulation. But there's no ability to understand things that are not the result of such physical stimulus, like light stimulating a retina and that stimulating a certain set of neurons in the brain in a certain way, such as ideas. What physical processes in the brain are associated with ideas like love, or emotions like love, or even more simpler ones like, the smell of a rose. Think about that. That something like, you say people smell the rose, they say that smells good, I like that smell, but you have no idea whether the smell that you associate with the rose is the same smell that somebody else associates with the rose. Or when you say, I like the color blue, what you call blue, you have no idea if it's exactly what somebody else calls blue. It's just that you've done a certain social interaction with another person who says, I call this blue, and you say, yeah, I call it blue too. But what you both mean by blue is no way to know if it's exactly the same. And you have no idea, and neuroscientists have no idea of whether or not, or what the physical substrate that gives rise to that. Because the concept of blue is not, or smell, or taste, or an idea like love, is not something which comes from outside, but is generated from the mind itself. So there's a small group, but an increasingly interesting group that has said we have to reverse this. Instead of looking for the physical substrate in the brain of what we perceive as subjective processes, we should look reverse and say, well, how does the generation of these ideas cause the brain to react in certain ways? In other words, instead of thinking that the ideas are generated by the brain, think about how the brain is generated by the need to generate ideas, by the development of ideas. And that right there is a very, I think, gets very clearly to the point of the direction science has to go. Reductionism would try and say, well, all our ideas, all our thoughts, from the very basic to the most lofty, are all epiphenomena of some type of physical activity going on in the brain. And if we can just break the brain down as reductionists into its basic elements and see how those things interact with each other, we can find the source of all ideas in the brain. And yet, it's obvious that ideas are not generated in the brain per se, but the brain was created to be at the service of our ideas. Now, you obviously need a brain to think, and we know that you can disrupt thinking by disrupting biochemical processes in the brain. That's what drugs do. But so there's a relationship there. But we keep looking at it, science keeps looking at it from the standpoint of that ideas are an epiphenomena of the biophysics of the brain, rather than turning it around and saying, well, let's look at the ideas and see how the brain has to develop itself and function to be able to make it, to be able to obey those ideas. And this drives reductionists absolutely crazy. And if you actually follow any of these reductionists, their arguments, and you pin them down on this, they will always react and say, well, ultimately, what you're saying is what they call God in the gaps. It's just something you can't explain, and you're saying, well, this is God. So you don't have to explain it. But the fact of the matter is, if the universe is an evolving system, which it is, and it's evolving in such a way that it creates new potentials as it develops, then it's just like the human mind, a creative process. The human mind creates new ideas which were never existed before. And every one of us does that. We create new ideas which are new to us individually, but then we also can create ideas which are new to mankind as a whole. And so the source of those ideas can't be just in the brain, because the brain doesn't biologically, physically change when a new idea is created. So it's a kind of living process which has the capability of being at the service of a creative process, which is the development of the human mind. And that occurs in a completely different realm. That might be a little hard to follow, but I think it's the only direction we have to go in if we're going to advance science.
Yeah, I think that was marvelous. So let's open up to discussion. We have a lot of people involved.